course, in this video, we are going to continue looking through probability distributions, and we're going to look at another couple of discrete distributions. We're going to look at the binomial and the Poisson distribution. Now, if you remember in the last video, we kind of looked at probability distributions in quite a lot of detail. And we basically said a probability distribution is a way of linking an outcome with its associated probability. Okay, and there's a few ways that you can do it. Like number one, you can just simply draw a table. We also looked at these things called piecewise functions. And we also looked at this idea of a probability mass function as well, which is literally just a definition. It's just literally a function which links an outcome with its associated probability. We also looked at things like expectation and variance as well. And the reason why we said that expectation is called expectation, you think of it as kind of like the mean. Okay, but it's not the mean because you're no longer working with data. Okay, you're working with outcomes and the associated probability. There's no data there anymore. So therefore you ask the question, well, okay, instead of saying, well, what is the mean? What is the average? You say, what value do I expect to get? Okay, so they're very similar, but they're subtly different, but they are different, and it's important to know that. Okay, and then we also looked at variance as well. And if you remember as well, we also looked at our first type of distribution, which was the uniform distribution, which was basically this situation if you had outcomes where each outcome was equally likely, in other words, their probability were uniform, that means it's a uniform distribution. Now, we're going to start looking at our second discrete distribution, and this is actually a really important one. So what I want you to do, and I actually want you to do this with me, I want you to go away and I want you to actually grab something kind of soft. Now, if you've got a beanbag, great. Usually if I was in the class, I'd kind of hand out beanbags, but if you're doing this at home, just grab something soft. So here I've just got a bit of fabric, which has got a little bit of weight to it. And I want you to put a bit of paper in front of you, and I want you to kind of take a few steps back. Okay, then I want you to pause the video and I want you to throw this sort of item 5 times. Okay, and I want you to count in each of those 5 throws, how many times does your item land on the bit of paper? Okay, so pause that now. Okay, take a step back, throw your item, see if it lands on the bit of paper, and do it 5 times, and then you should come back with a number. Okay. Okay, so hopefully you've had an opportunity to do that, okay? And you should have a number currently sitting in your head. So what I want you to do is draw out a table which I've got on the screen here. Okay, so this table basically corresponds to the amount of times that your beanbag or your item landed on the bit of paper in the set of 5 throws. So obviously, the minimum number of times it could land on the paper is 0. It didn't land on there at all. And the maximum number you could get is 5. In other words, it landed on every single throw. Okay, so you should have a number in your head. And basically what I want you to do is just fill in a 1. So frequency is how many times that comes up. So I did it just now, okay? And it landed 3 times on my bit of paper. So I'm going to put a 1 there. Okay. Now I want you to pause the video and I want you to do exactly the same thing as you just did. So throw the item 5 times and see how many of those times it lands on the bit of paper. So pause the video and do that now. Okay, so I just did it again, okay, and I got, well, it's 1 time on 3, and this time I got it on 2. Now what I want you to do is actually stop and pause the video for a second and do this about 10, 15, maybe 20 times. So basically throw the beanbag 5 times, count how many times it lands on the bit of paper. So let's say I do it another 5 times, lands on the bit of paper once in those 5 throws now, okay? So put a tally there, okay? And then do it again, okay? And I want you to repeat that about 20 times. So you basically should start up with a frequency distribution. Okay, so I did that 20 times, okay? And I've added them all together and I get something that looks like this. In fact, I only did it 19 times, so let's just suppose I did it 1 more time and I got it landing on 1 twice, okay? So there you go. So basically, this is basically a frequency distribution. Now, what I want you to do is try and convert this into a probability distribution. So before we do so, let's come back to our slides, okay? And let's just think through exactly what these definitions mean. So first of all, in the context of us throwing this item onto our bit of paper in a set of 5 throws, let's think about what variable, discrete variable, fixed trials, success or failure, independent binomial means in the context of what we've just done. Okay, so you can either pause the video and have a go at trying to answer those questions yourself, or I'm actually just going to talk through them with you. Okay, so here we go. So variable. So what's the variable in this case? Well, the variable is the number of times that our beanbag, our item, lands on the bit of paper. That's the thing which can change each time. Okay, it's the number of times it lands on the bit of paper. Okay, so it could land twice one time, 5 another time, and then 3 another time. Okay, so it's changing. So the number of times is changing. Why is it discrete? Well, because it can only land an integer number times. It can't land 3.5 times. It can only land 0, 1, 2, 3, 4, or 5 times. Okay, so it can only land an integer number of times on the bit of paper. What do I mean by fixed trials then? Well, the thing is, we're throwing the beanbag 5 times. So every single time we do the experiment, we are doing a fixed number of trials. It's 5. So it's not like one time we throw it 6 times, another time we only throw it 3 times. We're basically throwing it 5 times. Every single experiment, we're throwing it 5 times. Okay, so it's fixed. It's not changing. Now, what do I mean by success or failure? Well, this really is why it's called a binomial distribution. Okay, if you actually have a look at the word binomial, okay, in this context, so if I write down the word binomial, you notice that it's kind of made up of 2 different words. It's made up of bi and it's made up of nomial. Well, bi basically means 2, okay? And nomial, well, in the case of this, it means named thing. In the case of this, because we're dealing with probability, it means outcomes. Okay, so the reason why it's called binomial is because there are only 2 outcomes. Now, if you think about it, when we threw this beanbag on the bit of paper, right, it could land once, it could land twice, it might not land at all, it might land 5 times, so it can kind of change. So how can you get 2 outcomes from this? Well, if you think about it, each time we throw that beanbag, each time we throw this item, it can either result in a success, i.e. it lands on the bit of paper, or a failure, i.e. it doesn't land on the bit of paper, okay? So the reason why it's called binomial is because the 2 outcomes are either success or they are a failure, okay? It either lands on the bit of paper or it doesn't. And this is the characteristic of a binomial situation. Now, if you think about it, most things in life kind of follow either a success or failure. If you think about most situations in life as either something happens or it doesn't happen. Either you get a success or you get a failure. Even things like our uniform distribution when we're dealing with rolling that dice, yeah? You know, okay, there were 6 possible outcomes. You could get the numbers 1 through to 6. Or you might get even numbers or odd numbers, right? But you can still think about those as a success or failure. For example, if I roll the dice, I'm going to consider it success if I get a 4, otherwise it's a failure. Okay, so I'm basically looking at an event. If I want to look at an event happening, I consider that a success. Otherwise, if it doesn't happen, it's a failure. So that's really at the heart of what binomial distributions are all about. It's something that results in either a success or a failure. So in other words, in this case, does the beanbag land on that bit of paper or doesn't it? Okay. Now, independent. Now, this is one of the characteristics of a binomial distribution. Effectively, it means that each throw is not influenced by the previous throw. So every single time I take my beanbag and I throw it, okay, it's not then going to influence the chance of it landing on the bit of paper the next time I throw it, okay? So I've just thrown it just now. If I throw it again, it's not going to be affected by the previous throws, okay? So whether it lands on the bit of paper or not is not affected by the previous throws, okay? So that's what I mean by independent. Now, strictly speaking, you could argue that they are dependent because obviously the more you throw the beanbag, the more you get used to its weight, the more you get used to how much pressure you have to, or how much force you have to put behind the throw, the more you kind of get your eye in. So there is a kind of training or learning effect that is going on in the background. But if this was strictly speaking a binomial distribution, if we're just modeling it, making it simple, then absolutely we would just say that each throw is not influenced by the previous throws. And so what makes a binomial a binomial? Well, it's a random variable with 2 outcomes, and the 2 outcomes are success or failure. Okay, so these are kind of the characteristics of a binomial distribution. So basically, if I now look at the parameters, so I've defined my random variable on the top, and you should always do this when you're dealing with random variables. You should always say, well, actually, instead of writing the number of times the beanbag lands on a bit of paper in a set of 5 throws, I'm just going to let X represent all of that. So it's just using notation. We talked about the notation in the last video. So what are the parameters then? What were the parameters that we had when we just threw this beanbag? Well, first of all, are you happy? You need to think about the number of trials. You need to think about the number of times that you're actually throwing that beanbag. And as we've seen in the last slide, the number of times you throw the beanbag is fixed. Okay, so every single experiment, you need to keep the number of times you're throwing the beanbag the same. It needs to be fixed. So that's the first parameter that we're dealing with. But you also, so we basically give that the letter n. Okay, so the number of trials, the number of times you're doing it, we give that the letter n, and in this case it's 5. Okay. The other parameter you need to think about is the probability of success. In other words, what is the chance of you actually being able to get it on the beanbag? Well, you can work this out from a frequency distribution. Okay, so if I take this frequency distribution that I've got here, okay, you can see that the most likely outcome is the outcome or the event which has the most number of throws. Okay, so I basically, in a set of 5 throws, I got 3 successes. So in other words, I managed to get this piece of this beanbag landing on the bit of paper 3 times in every set of 5 throws. That was the most popular outcome. Okay, so in that case then, I'm basically saying that the probability of success should be 3 in every 5. Okay, so 3 in every 5, because I'm throwing it 5 times and I'm expecting 3 of those to result in a success. So I could write that as 3 over 5, or I could write it as 0.6. So that there would be the probability of success. Okay, and I can work that out from a frequency distribution. Okay, so I know that the probability of success is 0.6. In other words, in every 5 throws, I am expecting 3 of those to result in a success. Okay, so I give this the letter P. That's my other parameter. So I basically have 2 parameters. Number 1, the number of trials. How many times am I actually throwing my beanbag in this case? And then the second one is, what is the probability that I'm actually going to get it landing on that beanbag? Well, 0.6 basically says that 3 in every 5 should result in the beanbag landing on the bit of paper. Okay, so the way which I write this is like this. So it looks a bit weird, but it's just notation. So the x, remember, is my random variable. So x is defined at the top as the number of times the beanbag lands on the bit of paper in a set of 5 throws. This little squiggly sort of symbol here, this kind of wavy line, in this case, it just means is distributed. Okay, so x is distributed. That's what that squiggly line means. And the B is just basically short for binomial, because I know that it's following a binomial characteristic. Okay, we defined all those characteristics on the previous slide. Okay, so basically if all of these characteristics are met, you have a fixed number of trials, it can result in a success or failure, you've got a discrete random variable, and all the trials are independent of each other, then you can kind of say, well, okay, it's a binomial distribution, and I'm expecting 2 parameters, the number of trials and the probability of success. So therefore, I'm saying that x is distributed following a binomial distribution. That's what the first 3 symbols mean. And then in the brackets, I have the parameters which I'm dealing with. So just remember, the parameters are the features of this particular binomial distribution. In this case, it's the number of trials and the probability of success, so n and p. And it's always in that order. You can't swap the order around. So you can't have p first, then n. We always have the number of trials first, and the p is the probability of success. Okay, so that's really important. So in general, you have x is binomially distributed with n trials and a p chance of success. So the probability that goes here is always the chance of success. Never the chance of failure, always the chance of success. Okay, so hopefully that makes sense. So how then can I physically convert this situation here? So this situation here, how can I find the probability mass function? Okay, so remember the probability mass function says, here are my outcomes. I can have 0 successes, 1 success, 2 successes, 3 successes, 4 successes, or 5 successes. In other words, it can land 0 times, 1 time, 2 times, 3 times, 4 times, or all 5 times in a set of 5 throws. How can I find the associated probability? Well, I could do it from kind of experimental data, literally doing what I do, just literally throw this beanbag loads and loads of times and throw it like 5 times and do that loads and loads of times, and I basically build up a nice little frequency table. However, I think we can do it more logically, okay? Because if you think about it, if I write this down, so this here means the probability that x, i.e. the number of times the beanbag lands on the piece of paper in a set of 5 throws, is equal to 0. In other words, if I throw this beanbag 5 times, what is the probability that it doesn't land on that bit of paper at all? Okay, there's no successes. Well, if you think about it, if I visualize it, this is my beanbag. None of these, each of these sort of things here represent a different throw of my beanbag. Okay, so this is my first throw, second throw, third throw, fourth throw, and fifth throw. And if I put a cross through them, it means it doesn't land at all. Okay, so I just need to work out, well, how can I work out the probability of this happening? Well, if you think about it, that means that all 5 throws must result in a failure and there are no successes. Okay, so there are no successes. Okay, so the chance of success is 0.6. That happens no times. Hence, it's 0.6 times itself 0 times. Okay, so 0.6 to the power of 0. Okay. And there's got to be 5 failures, okay, because all 5 throws result in a failure. Well, if 0.6 is the chance of success, 0.4 has to be the chance of failure, because a failure plus a success has to be certain. Okay, it's either going to be a success or failure, can't be anything else. So it's got to add up to certainty. It's got to add up to 1. Okay. So therefore, I'm going to take 0.4 times 0.4 times 0.4 times 0.4 times 0.4, or 0.4 to the power 5. Why am I multiplying again? Just think. Just remember that I want all of these things to happen. In other words, it's an and situation, okay? So the first throw isn't a success, and the second throw isn't a success, and the third throw isn't a success, fourth throw isn't a success, and the fifth throw, it's not a success, okay? So therefore, I'm going to do 0.4 times itself 5 times, okay? Well, if I think about that, I also need to think about the ways in which I can get no successes from 5 trials. Now, this might not make sense in this case, because in this case, there's only one way of doing that, and I've written it down on the screen. It's just all of them are failures, okay? But I need to think, because I'm doing it from the perspective of a success, how many different ways are there of getting 0 successes from a set of 5 trials? Well, answer, we did that in the last sort of theme. It's 5 choose 0 ways. I'm doing it 5 times, so there's 5 possible options I could have, and I'm choosing 0 successes from that, okay? If I do the same for probability that x equals 1, this is basically saying again, if I take my beanbag and I throw it 5 times, so 1, 2, 3, 4, and 5, okay, if I throw it 5 times, what's the probability that one of those is a success? In other words, one of those actually physically lands on the bit of paper. Well, if you think about it, that basically means I have 1 success and 4 failures, okay? That's what that means there, that's what the symbol means there. So 1 success and the other 4 failures, okay? Well, the probability of getting 1 success is just 0.6, okay? So I'm going to take 0.6 and do it once, because I've only got 1 success there. But then the others are failures, so the probability of a failure is 0.4, and I've got 4 failures there, because it's going to be 5 minus 1, which leaves the 4 failures. So 4 failures is going to be 0.4 to the power of 4. But I also need to think about the number of ways of arranging these things. So the way which I've drawn it at the moment is in my 5 trials, the first trial, the first time I throw the beanbag, it results in a success, but then the other 4 are failures. But I don't know whether that could be true, okay? It could be true that the first is a failure, then the second is a success, and then the other 3 are failures. Or it might be that that success happens on the 3rd throw, or the success might happen on the 4th or the 5th throw, okay? So I need to think about the ways of getting 1 success from 5 possible throws. Well, that's just going to be 5 choose 1 ways, okay? If I just talk you through the second one and then the rest just kind of fall out nicely. So this basically says, what's the probability that if I throw my beanbag 5 times, what's the probability that 2 of those will result in a success? In other words, 2 of those will land on the bit of paper. Well, okay, I'm going to get 2 successes and 3 failures, right? 2 successes is going to be 0.6 to the power of 2, because 0.6 is the probability of success, and it's happening twice. And then the other 3 are failures. So the probability of a failure is 0.4, so it's 0.4 to the power of 3, okay? But I also need to think, just like the last examples, how many different ways are there of getting 2 successes in a set of 5 throws? How many different ways are there of choosing 2 successes in a set of 5 throws? Well, it's going to be 5 choose 2 ways. And are you happy it's going to be a similar kind of thing for probability that x equals 3, and for probability x equals 4, and for probability x equals 5? Okay, so it's a similar kind of thing. You need to think about 3 things when you're working out the probability of a binomial distribution. Number 1, what's the probability of getting that many successes? Number 2, what's the probability of getting that many failures? And number 3, how many ways are there of choosing that many successes from that many trials? Okay. So in general then, what I can say is that I should have to multiply these probabilities together, okay? Remember, this second thing here is the probability of success. So what's the probability of getting that many successes? And I want that many failures. So what's the probability of getting that many failures? And then I also need to consider how many different ways are there of getting that many successes and that many failures. That's what the 5 choose n is doing on the end, okay? 5 choose r. So in general then, if I go through and actually work out what the probabilities of each of these are, if I actually stick these into my calculator, you can see that these are the probabilities that come along on the table on the top. So this is my probability mass function, okay? So in general then, if I just have a binomial distribution like this, so x is binomially distributed with that many number of trials and that probability of success, I can basically say that the probability mass function, so little case f of x, should be given as n, and then x is the number of successes you're interested in. So what's the probability that x equals x? N is the number of trials, x is the number of successes. So it's n choose x, times by the probability of success, x many times, times by the probability of failure for the remaining number of trials. Okay. Now, if I don't want to write 1 minus p, okay, because I've let p represent a success, then 1 minus p, fairly obviously, will represent a failure. So what comes after p in the alphabet? Well, we just say q. Okay, so q is basically the probability of a failure, p is the probability of a success. So if you didn't want to write 1 minus p, you could always just write q as notation, that's fine as well. Okay, so hopefully that makes sense. Okay, so what does the probability mass function actually physically look like? So we've got the probability mass function along the top here, it's in the table, but what does it physically look like? What if we wanted to sketch it? Well, what we can do is basically have all of the different possible outcomes along the x-axis. These are all my outcomes. I can have 0 outcomes, 0 successes, 1 success, 2 success, 3 successes, 4 or 5 successes. And along the y-axis, I can have the probability of that success happening. So if I actually sketch this, you notice that I get discrete bars, okay? So these kind of lines just represent, this is the probability of each of these outcomes happening. Because fairly obviously, all of the other outcomes have to be 0, okay? I can't have an outcome of 0.2 or 0.7 or 1.6 or 3.2, okay? So I can't have probabilities happening, or I can't have outcomes happening in between these things. Hence, in that case, the probability is just 0, okay? So it's just a flat line. But then these heights correspond to the probabilities of these, okay? So hopefully that makes sense. So you notice that this kind of shape is a nice kind of curved shape. The most likely outcome is the outcome with the highest bar. It's in the middle, in this case 3. And then the kind of probabilities of the outcomes each side of that kind of drop off. Okay, so the probabilities decrease each side, right? Now you can actually play around with this using this GeoGebra panel here. So let me just open this GeoGebra link up. Okay, so basically at the moment what I've got is a different probability distribution here. I've basically got a binomial distribution with a parameter of number of trials of 10 and the probability of success is 0.5. Now look what happens to the probability distribution as I change these two parameters, okay? So as I change the number of trials, can you see that all that happens is I still get this shape, I just get more bars. So I still get this kind of curved shape where there's a kind of peak in the middle and then it kind of drops off each side, okay? So it drops off each side. So it drops on the left-hand side, it drops off each side. That just basically represents that the most likely outcomes are kind of somewhere around here, and the less likely outcomes are out here and out here. Okay, so the probability decreases. But if I now change the probability of success, maybe if I decrease the number of trials to maybe something like 8, if I fiddle around with the probability of success, because you notice at the moment, this is a nice kind of symmetrical distribution, okay? It's not skewed at all, and we talked about skews in the last video, in the first videos at least. So if I change this, at the moment the probability is 0.5. In other words, there's an even chance of a success as there is a failure. But if I bias it so that there is more chance of success, in other words, I increase the chance of success, look what happens to my distribution. Okay, can you see now it becomes skewed? And it becomes skewed negatively. In other words, the outliers occur over here, and most kind of outcomes should occur somewhere close to 7 or 8, because there's a high chance of success happening, which means that the majority of these trials should result in a success. Whereas if I skew it so that there's more chance of failure than success, in other words, it's less likely to happen, can you see, again, I get this nice shape happening, but this time it's positively skewed. So most outcomes are kind of quite low. In other words, I'm more likely to get a low number of successes in these 8 trials. And again, if I just increase this, all this is doing is it's just giving me more bars, okay? So the probability is basically defining the skew. okay? And you can see that makes total sense, because if I have a low probability, it means that I'm expecting very few of these trials to result in a success. Whereas if I have a high probability of success, I'm expecting more of these trials. A high number of trials should result in success. So what about the cumulative distribution function then? Well, basically all I need to do is just add these up as I go along. So just remember, cumulative distribution function means add them up as you go along. So I kind of get this step function here. So it's nothing really that interesting, apart from the fact that the steps kind of grow higher in the middle, corresponding to the fact that that's where the majority of successes should lie. Okay. Now you may want to pause the video and actually have a go at some of these, okay? So for example, what's the probability that x equals 4? I can tell you straight away, is about 26%. It's 0.2592, okay? If you want the probability that x is less than or equal to 2, it's going to be the probability that x equals 0, plus the probability that x equals 1, plus the probability that x equals 2, because it basically means less than or equal to. But you notice for question 3, it's strictly asking the question, what's the probability that x is less than 2? In other words, you don't include 2, okay? So if you don't include the 2, it's just going to basically be the probability that x equals 0 plus the probability that x equals 1. So in other words, these two probabilities added together now, okay? But you notice if I want, for example, what's the probability that x is greater than 2, okay? What I could do is 1 minus the thing which I don't want. Well, the thing which I don't want is 2 or less, okay? So the thing which I do want is 2 or more. The thing which I don't want is 2 or less. So if I do 1 minus that, in other words, 1 minus the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2, that will give me the probability that x is greater than 2, okay? Because you notice all of these probabilities have to add up to certainty. I'm expecting at least one of these outcomes, so therefore if I add them all together, I should get certainty. Now we'll just point this one out. What's the probability that x is greater than or equal to 1.3? Even though 1.3 is not an allowed outcome, like if I throw this beanbag, it won't land 1.3 times. It will never do that. It will land an integer number of times. So I can't have 1.3 as a possible outcome. But that's okay, Because all I'm going to interpret this as is what outcomes occur greater than or equal to 1.3. Answer, 2, 3, 4 or 5 successes, okay? So basically greater than or equal to 1.3, don't get put off by the fact I put 1.3 there and you can't have 1.3 as the number of successes or the number of times this results in a successful outcome. But what you can have is all of the outcomes greater than or equal to 1.3. So 2, 3, 4 or 5, okay? So don't get put off by that. Now just have a look at this. Find the probability that x is greater than 5. Well, are you happy that I can't have any successes more than 5? Like I'm only throwing this beanbag 5 times. It can't land on the bit of paper more than 5 times. It's physically impossible. So therefore, if something's impossible, that probability should be 0, okay? Now, what should the expectation and variance be of a binomial distribution? Well, are you happy that expectation just means what is the expected value? What is the expected number of landings in a set of 5 throws with a 0.6 chance of success? Well, fairly obviously, it should be the one with the highest bar, right? So if you look at this, the probability of success is 60%, okay? That means there's a 60% success rate, okay? So therefore, in 5 throws, I expect 60% of them should result in a success, okay? So 60% of 5, that should give me 3. In other words, the way to calculate expectation is just simply by taking the number of trials you're doing, and timesing by the associated probability of success, okay? So you just take the number of trials, which is n, multiply it by p, which is the probability of success, and you'll get your expectation. Now you notice that makes sense because if you have a look, this is the one which has the highest probability of occurring, okay? So 3 is the outcome with the highest probability of occurring, so that makes sense, okay? Now, if you consider that x is a series of single trials that result in either a success or failure, then instead of considering 5 throws in a row, let us consider each throw as a separate trial, okay? So this is how we actually derive the formula for expectation and variance. This is a proof, if you like. So basically what I'm doing here, what I've got you to think about is when you throw your beanbag, you're basically throwing it 5 times. And I've got you to think about those 5 throws as kind of like one experiment. But instead of thinking it as one experiment, where that experiment consists of 5 individual trials, let's break it down so that we break it down into 5 separate trials instead. And we look at each trial individually. So we basically look at each throw as an individual experiment instead of the 5 throws as the entire experiment. So okay, let's have a look at this. Well, instead of using x, I think we need to change the notation slightly. So I'm going to use y, and I'm going to number them, okay? So the little 1, 2, 3, 4, and 5 corresponds to which throw we're doing. So y1 corresponds to throw 1, y2 corresponds to throw 2, etc., 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 okay? So in which case then, I can say that x, which remember, x is 5 throws in a row, so x was the original 5 throws that we were doing in a row, well, it consists of 5 individual throws, okay? So the y1, y2, y3, y4, y5, they're the actual individual throws. X is the 5 throws put together, okay? So in general then, I can say that x is made up of all of these individual throws, okay? Right the way through to however many trials I've got. So in which case then, if I consider any general trial, any general throw, so let's maybe consider the 3rd throw or the 5th throw or the 7th throw. If I just consider one individual throw, then are you happy the number of times I'm doing it is 1? Okay, so 1 is the number of times I'm doing it because I'm only throwing once, right? Because I'm considering it individually. And it's still got the same probability of success. So it's still got the same probability that it will actually land on the bit of paper, okay? Now, in this case, if you have a binomial distribution with the number of trials equal to 1, we give that a special name. We call it the Bernoulli distribution, okay? So the Bernoulli distribution is just a one-trial binomial distribution, okay? So basically, there's 2 things that can happen with this single trial now. Either it doesn't land at all. In other words, the probability that this throw doesn't land should be equal to this. And I'm just literally using the same idea as I was for my probability mass function for my original binomial distribution. It's just now I'm considering it as a single throw where n is 1 and p is still the probability of success, okay? So there's 2 things that can happen. Either it doesn't land, okay? Well, in that case, if I actually work this out, 1 choose 0 is 1, p to the power of 0 is 1, times that by q to the power of 1, well, that should just result in q. In other words, the probability that it doesn't land on the bit of paper should just be equal to the probability of whatever that failure is. And that makes sense logically, right? But the other thing that can happen is that it does land, okay? So in other words, the probability that yi equals 1, in other words, the probability that throw does actually land on the bit of paper, so it results in 1 success, okay? Well, in that case, if I work this out, it's 1 choose 1 times p to the power of 1 times q to the power of 0, that's just p. And that makes total sense, right? So first thing is if I get a failure, okay, that's q, and the next option that I can have is if I get a success, okay, and that's p. So in other words, what I can say then is if I want to work out the expectation, just using my knowledge of expectations of discrete random variables, it should just be the sum of each outcome times the associated probability. That's all that notation means. It's the sum of each outcome times their associated probability. Well, in this case, there's only 2 outcomes. Either it doesn't land any times or it lands once. That's the only thing which can happen in a throw, in an individual throw. So therefore, if I do that, I get 0, because that's no successes, so it doesn't land, times the probability it doesn't land, so 0 times q, plus 1 times p. Okay, so in other words, that should just come out as p. But basically, just remember, this is just the expectation of one single throw. What about now if I put this together so that it kind of is now the true random variable? In other words, 5 throws in a row or 10 throws in a row, or however many trials I'm doing, n trials, okay? Well, if I do that, I know that the expectation of getting each throw resulting in success, the expectation of each throw should just be p. So in other words, if I'm doing these throws n times, the expectation of all of that should just be the expectation of all of those things. Well, this is the expectation of basically loads of p's being added together. How many p's am I adding together? Well, I have n throws, so it's just going to be n times p. Okay, so the expectation of x should just be n, which is the number of trials, times the probability of success. So it's just n times p. What about variance then? We're doing a very similar kind of thing. So bringing up what we did for expectation, the probability of getting no successes is q, and the probability of getting 1 success is p on each individual throw. So how would I work out variance? Well, just remember the formula for variance is just given by this. It's e of y squared minus e of y all squared. Well, are you happy that I've already got the expectation of that particular throw? It's just p. I worked that out in the last kind of couple of slides. And I know that the expectation of y squared should just be the sum of y squared times the associated probability. I'm just basically substituting y for y squared there. So if I do that, I'll have 0 squared times q, that's basically no successes times the associated probability, plus 1 squared times p, that's basically 1 success squared times the associated probability, and I've got to take away p squared. So in other words, I get 0 plus p minus p squared. So I get p minus p squared. So therefore, the variance of each individual throw, if I factorize out, should be p times 1 minus p, where 1 minus p is just q. Yeah? Because that's just a probability of failure. Okay, so therefore the variance of each individual throw, so every single time I throw this beanbag, the variance of that throw should just be the probability of success times the probability of failure. But of course, now if I put it together with my proper distribution, my proper random variable, my random variable is made up of 5 throws. Okay, so 5 individual throws or 10 individual throws, or in general, n individual throws. So in other words, if I want to find the variance of this thing, I know by definition that with a binomial distribution, each throw is independent of all the other throws. So therefore, the variance should just be added all together and there's no covariance term at the end. So therefore, I'm just going to get loads of PQs added together. Well, how many PQs am I adding together? Answer, however many throws I do. So NPQ, okay? So therefore, the variance should be M times P times Q. So there you go, there's an expectation and proof formula. So first of all, if you have a binomial distribution, so X is binomially distributed with a fixed number of trials and a probability of success. This is the probability mass function. We talked through where that came from. Okay, now I apologize for the contrast just because I'm using my chroma key and it's not showing up properly. This is the expectation, so it's just n times p, and this is the variance, which is n times p times q. Okay. Now you may wish to have a go at some of these questions. So basically just using the formulas which we derived on that last slide, okay? So these formulas which we derived on the last slide for a binomial distribution, you should now be able to answer these two questions. Now the difference between these two questions, this question here is kind of more of an introductory question. It's kind of stating what the binomial distribution is, what the parameters are, and then it's just asking you to find standard probabilities and expectations and variances. Nice and straightforward, just using the formulas. Second question is actually exactly the same thing as the first, it's just that it is more wordy. Okay, so because it's more wordy, you have to pull out what the probability of success is, and you also need to pull out what the number of trials are. So in this case, it's actually very, very straightforward and easy. You can see that it's known that 35 out of 100 patients will suffer from a headache. So actually the way which I would do this, if I write this down, first things first, I'm going to have to actually define my random variable. So I'm just going to call my random variable x, okay? And I'm actually going to define this. So x is the number of patients with headaches. So in other words, if somebody gets a headache, I'm going to consider that a successful outcome, okay? And whether it's positive or not doesn't matter, okay? So whether it's a positive outcome or not, it doesn't really matter. It's just basically, it is a success, okay, if they get a headache. So number of patients with headaches. Okay, now let's have a look. So I've basically got x, and I know it's going to be binomially distributed because are you happy? They either get a headache or they don't. So therefore it's a success or failure. So it's going to be binomially distributed. Now, what is the number of trials? Well, if you have a look down the bottom, you're told 12 patients are given the injection. So the number of trials has got to be 12. And then you're also told the probability of success because you're told 35 out of 100 patients will suffer from headaches. So therefore this is going to be 0.35. So basically, now I've got that down, actually the rest of this is very, very straightforward. Well, what's the expectation? Well, the expectation is just simply going to be n times p, so it's going to be 12 times 0.35. Work that out. What's the standard deviation? Well, I know that the variance is going to be n times p times q, so 12 times 0.35 times 0.65, okay, that's my q. But if I want to find the standard deviation of this, just remember standard deviation is just the square root of variance. So I'm going to have to square root all of that, okay? And if you want the probability that x is greater than or equal to 4, what's the probability that 4 or more of these patients will suffer from headaches? Well, the probability that x is greater than 4 or equal to 4, because I want greater than or equal to 4, what's the probability that 4 or more, so that's greater than or equal to 4, okay? Well, that can just be 1 minus the probability that x is less than 4. In other words, I can go through here and I can calculate, well, okay, what's the probability that x equals 0? What's the probability that x equals 1? What's the probability that x equals 2? And what's the probability that x equals 3? Okay, so I can go through there, physically calculate each of those probabilities, and then do 1 minus that, and I'll end up with the thing which I want. Now, can I ask you, I'm going to ask you this week to do 2 things for your weekly task. This is the first one. So this is the first thing that I'm going to ask you. This question here, Eric and Ross are throwing skimming stones. The probability that a stone thrown by Eric will hop is 0.2, whereas the probability that Ross will get a hop is 0.1. Both boys throw 10 skimming stones. Determine the expectation and variance for Eric, expectation and variance for Ross, and the expectation and variance for the two boys. Okay, so I want you to do this. This is your first task for the weekly task this week. Okay. Now, let's move on to the second distribution we need to look at, okay? So let's quickly do this. It's the Poisson distribution. Now, I'm not actually going to go through this experiment together, but effectively, if you wanted to try this yourself, you could do it with a pulse, okay? So you could literally just find your pulse on your arm, okay? So literally just find your pulse on your arm, and then basically get your timer up on your phone, wait 10 seconds, and count the number of heartbeats that you have in 10 seconds, and do it 5 times. Then all I want you to do is just find the average number of beats for a 10-second period. So in other words, you should do this 10 times. So you do it 10 seconds, count the number of heartbeats, then do it again, another 10 seconds, count the number of heartbeats, do it again, and do that 5 times. You should then have 5 numbers written down, which correspond to the number of heartbeats for those 5 times. Take the average of those, and that should be the number which you have. So therefore, if X is the number of times your heart beats in a 10-second period, the expected heart rate will just be that many beats per second. So let's suppose I've done this, okay, I've done it 5 times, counted the number of heartbeats each time, and let's suppose that my expected heart rate is 10 beats per 10 seconds, okay? So I'm doing 10 beats per 10 seconds, okay? So now my question is, what if I changed it? Okay, previously I was asking for what was my heart rate in 10-second period. Now if I changed it, so I did it in a 20-second period instead, okay, how will this change? Okay, so again, if I do this again, count 20 seconds, count my heart rate, and do it 5 times, take the average, how will this change? How do I expect it to change? And in fact, I can do it again, so how can I do it in 30 seconds? So really what I'm doing here is building up this idea of a Poisson distribution. A Poisson distribution is something that happens with a given rate, okay? Now, because I'm changing the time interval, so basically the time interval is what matters here. The first time I did it, so the first time I took my heart rate, okay, I let it equal X, and that's basically the number of heart rates which I have in a 10-second period. But then I changed it, and I said, what if I change it to now be 20 seconds? Well, because I'm changing it, I'm having to change my random variable as well. So basically, X was the random variable that represents a number of heartbeats in 10 seconds. Now, Y represents the number of heartbeats in 20 seconds. And when I changed it again to 30 seconds, then I had to change the random variable. So basically, when I define a random variable for a Poisson distribution, I know we haven't talked really about what a Poisson distribution is yet in that much detail, but basically it's something that happens with a given rate, okay? And when I define my random variable for a Poisson distribution, I must always give the rate at which it's happening, okay? So basically, if I change the rate, so in this case I started with 10 seconds, then I changed it to 20 seconds, because I'm changing the rate, because the definition of a Poisson distribution, the definition for the random variable of a Poisson distribution has a rate baked in. So I need to give the rate always. Then if I change the rate, I get a different random variable. Okay, so hopefully that makes sense. Basically, because when I'm defining a random variable for a Poisson distribution, it has a rate baked in. If I change that rate, then I need to change the definition of my random variable. So let's just quickly talk through the different definitions for these words for the Poisson distribution, okay? So first things first, what does the variable mean in the context of actually taking our heart rate? Well, the variable is just simply the number of heart rates within a given time period. So it could be 10 seconds, 20 seconds, 30 seconds, a minute, a day, a week, whatever it might be, okay? Why is it discrete? Well, you can only have an integer number of heart rates within the given set, okay? So for example, if I said, well, okay, I timed it for 10 seconds, I can only have like an integer number of heart rates which happen within that given time interval. Okay, I can't have like half a heartbeat or 3/4 of a heartbeat. I can only have an integer number of heartbeats within that given time period. Why is it happening at a constant rate? Well, basically what I'm saying here is that if I looked at a 10-second period, then the idea is I should basically have the same number of heart rates in this 10-second period as if I then looked a little bit later and looked at another 10-second period. So basically, if I'm looking at two separate 10-second periods, the idea is that the number of heartbeats should be the same regardless of when I look at that 10-second period. So if I start counting now, wait for 10 seconds and take my heartbeat, and then if I wait 2 minutes time and then do another wait for another 10-second interval and count the number of heartbeats, the idea is that it should still be the same number. It should still happen at a constant rate. What do I mean by unique? Well, unique in this case just means that two or more events cannot occur at exactly the same time. In other words, my heart can't beat twice at the same time, right? It's only beating once at the same time. Independent, well, each set of heartbeats is not influenced by another set of heartbeats. So if I look at one set of 10 seconds and count the number of heartbeats, that's not going to then influence the number of heartbeats I'm going to get on another set of 10 seconds, okay? Why is it Poisson? Well, Poisson distribution is quite simply a random variable that occurs at a constant rate, and it must be a discrete random variable. So basically, if I walk out and if I go and find something that happens at a constant rate and it results in a discrete outcome, then I can say it's distributed using a Poisson distribution. Okay. Now, if you think about it, there's a few examples of a Poisson distribution. Okay. So I've given an example with heart rate. It could be, for example, the number of times that people tweet within a given week. Okay. It could be if you walk out on the street and count the number of cars which pass your particular position in a given minute. Okay. These are all examples of Poisson distribution. They are basically things which are happening at a constant rate. Okay. So what are the parameters which we're interested in? Well, I think in this case, if we go back to our heartbeat example for a 10-second period, the only real parameters is just simply the number of beats which happen within that given time period. Now you could argue, well, surely the time period is also a parameter of the Poisson distribution. But if you think about it, the way which we define our random variable, so our random variable is defined with that time period baked in. Okay, so time period is automatically baked in to the definition of that random variable. Okay, so if I'm talking about 7 beats for every 10 seconds, I get lambda equals 7. So lambda is basically the letter which we represent, it's the Greek letter, which is representing the rate at which something has happened in this given time interval. Okay, so in general then I can say that x is distributed using a Poisson distribution. Notice that we use PO for distribution. Reason being is if I just put a P, I could confuse that with the probability of an event happening. So I put PO for Poisson distribution, and then the parameter is lambda. That corresponds to the rate at which it happens, okay? So since the rate is constant, then I have to change these things, okay? So for example, when I come back here, okay, I said first of all, x is the number of heartbeats in a 10-second period. So let's suppose I have x is distributed with a Poisson distribution, and let's suppose the rate is 7, okay? Well, if I change my distribution to be, let's say, y, which is the number of heartbeats in 20 seconds, so I'm changing the rate, well, then I'm also going to have to change the rate down here as well. But because it's happening at a constant rate, it basically means that 7 should just change to, you guessed it, 14, okay? And if I look at z, so again, I changed my rate to be 30 seconds instead of 10 or 20 seconds, then again, that rate should now be 21. So in other words, the rate at which it's happening is reflected if I change the time interval that I'm looking at, okay? So hopefully that makes sense. So you must define the time period when and the rate when stating the random variable. So when you actually write the random variable down up here at the top here, you must tell me how long I'm looking at. You must define that time period, because otherwise it's not valid. Okay. So this is basically how I work out the probabilities. Now I'm not going to tell you for the moment how to work out the probabilities. There is a proof of that coming up later on. Okay, but basically the idea is it's a similar kind of idea as a binomial distribution. The most likely outcome should be somewhere in the middle, and it should lie close to what the true rate should be. So in this case, I'm saying that the most likely outcome are 7 heartbeats in a 10-second period. And then each side of that, the probability drops off dramatically, okay? So the probability of getting 4 heartbeats in a 10-second period is much lower, okay? Or the probability of getting 10 heartbeats in a 10-second period, again, it's much lower, Okay, so if I'm going to plot this on a graph, I again get something that looks like this. This is familiar, okay? This looks just like a binomial distribution. The idea is I have discrete bars, I have discrete outcomes. That's the reason why I've got the bars here. And the idea is the most likely outcomes occur in the middle, and then the probabilities drop off to represent the fact that outcomes further away from the rate, from the most likely rate or the most likely outcome, are going to be less likely. Okay, now I could play around with this if I like. But effectively, all this is going to do is just move the distribution left or right. Okay, so if I just quickly show you, what I can do is actually change the rate. And you can see by changing the rate, all I'm basically doing is just changing the location of this distribution. Now, in general, this distribution is nearly always going to be symmetric. Okay, except if that rate is low. Okay, so if I got a low rate here, this is still symmetric. It's just that I can't have any outcome which is less than 0. Can't have fewer than 0 successes. Okay, so basically just by changing this will always be symmetric. It follows the same kind of shape as a binomial distribution. Okay, and it looks quite nice and it looks quite straightforward. Okay, but you notice that because this looks just like a binomial distribution, then I can notice a really important pattern. So the Poisson distribution looks like the PMF of a binomial distribution. So what's going on here? Well, in actual fact, if I increase the number of trials of the binomial distribution, and if I reduce the probability of success down, okay, then it basically means that it approaches a Poisson distribution. So basically, as I increase the number of trials of a binomial distribution, it should approach a Poisson distribution. So in actual fact, these two things, the binomial and the Poisson distribution, are pretty much the same, okay? They're pretty much the same distribution. It's just that if I increase the binomial distribution such that it has more and more trials, in other words, the number of trials, frankly, doesn't make sense to give that as a parameter anymore, then I get the binomial distribution. And that makes sense because if you think about it, the Poisson distribution only has a rate. It only has a rate of success within a given time interval. Whereas a binomial distribution also has the number of trials. So if I increase the number of trials of a binomial distribution, then actually it doesn't really matter that I need to consider the number of trials because I'm just doing it, right? Then I get a Poisson distribution by default because that doesn't have the number of trials as a parameter, okay? So basically for a binomial distribution, you have a fixed number of trials, which is n, and each trial has a fixed probability of success, which is p. That's the parameters of a binomial distribution, okay? And I can write it like so. Okay, so let's suppose I increase the number of trials. Okay, so let's suppose I did 1,000 trials every single day, because we've just seen that if I increase the number of trials of a binomial distribution, I should approach a Poisson distribution. Okay, so if I do a really big number of trials, if I do 1,000 trials each day, and let's say the probability of success is relatively small, let's say it's about 0.3, okay, then I can say that the average success rate per day should be given by this, okay. Now I just want to play on this idea a little bit. The idea is I'm trying to make a binomial distribution approach a Poisson distribution as much as possible. Well, I've just seen the binomial distribution. I do have an average, I do have an expectation. And the way which I get that is n times by p, okay? Whereas a Poisson distribution only has one parameter. It just has the rate of success, okay? So basically, if I'm thinking about a binomial distribution, but kind of with Poisson glasses on, trying to view it with a Poisson point of view, then what I'm basically saying is if I've got a large number of trials, and this is my probability of success, then I can say my success rate should be 0.3 out of the 1,000 trials every single day. So 0.3 of the 1,000 trials. In other words, 30% of the 1,000 trials per day, okay? Because it's got per day in here. So therefore I can say that lambda should just be n times p, which is the expectation. So if I want to work out the success rate of a binomial distribution, it's a similar kind of way in which I work out the expectation. But imagine now that all we know is lambda, like we do with the Poisson distribution. Imagine we only know this rate and we don't know how we calculated it. So we can assume there have been a large number of trials, okay, that's an assumption which is valid, but we don't know the exact number, okay? So in that case, we're basically meeting the condition that the number of trials is approaching infinity. Okay, Maybe we don't know the exact probability of success. So all we know, remember, is the success rate, which we've got up here. So let's say it's 300, okay? So let's say we've got 300 successes every single day. We can assume there's a large number of trials that have taken place, and we don't know the exact probability of success for each trial. So therefore, if we wanted to work out the probability of success, just using this formula that we've just derived, we can basically say that the probability of success should be the success rate divided by the number of trials which we've had. Does that make sense? Okay. If you're basically saying that the success rate is 300 trials every single day, then if you can divide by the number of trials which you've had, that will give you the probability of success. Okay. So in other words, what I'm doing here is kind of working backwards. I'm saying, imagine we don't know what the binomial distribution parameters were, but we did know this. Okay. So we have rate defined as this. And we've just said that if we want to find the probability of success, it's just the success rate divided by the number of trials, okay? So, therefore, if I take this, what I can say is I'm changing P to be this, okay? It's the success rate divided by the number of trials, okay? So therefore, if I work out the probability mass function of a binomial distribution, it's this. And if I substitute P with lambda over n, okay, then I can write it like this, okay? Well, actually, no, before I need to do that, I'm going to write everything in terms of n and mp. So basically taking the n choose x, and I've written it out formally, so rather than writing n choose x, I've used the factorial notation, and also I've written q as the 1 minus p. So now what I can do is actually replace p with this lambda over n, because I now know that lambda over n is my success rate divided by the number of trials I have. Okay, so what I'm trying to do here, just in case you're kind of not quite following the reasoning behind this, I'm trying to find the probability mass function of a Poisson distribution, okay? So therefore, after a bit of rearranging, okay, after a bit of sort of factorizing, things like that, I basically get this, okay? So let's have a look at this then. Because we've got a large number of trials, and the probability of mass function should basically be the limiting case of this binomial distribution. So this is still a binomial probability mass function. It's just that I'm considering it in terms of rate. I'm being deliberately ambiguous. I'm being deliberately kind of facetious, I guess. I'm basically considering it in terms of a rate and the number of trials, and this is basically what I get. So these two things, this thing which we derived before and this thing down here, they are still the same. It's just that I'm writing lambda as the rate of success, okay? So if I want to consider everything in terms of a rate rather than n and p, I can do this. Now I've just seen that the Poisson distribution is just the binomial distribution as n increases, so as n approaches infinity, so as I increase more and more trials, okay? So in that case then, I just need to consider what each part of this means, okay? Now, I know lambda and x are going to be constant, so the success rate has got to be constant, and the number of successes has also got to be constant for this, because I want to work out what's the probability of getting this many successes. That's constant. I also know that lambda, the success rate, is going to be constant as well. So therefore, I can say that anything that's constant, I can pull it out the front. So in other words, this term here, this term in the middle, because it's constant, I can just pull it out the front of the limit. It's not going to change the limit at all. It's the way that limits work, okay? So let's consider each term. Let's first of all consider the limit of the first term here. Well, basically, if I expand this out, I get n factorial, which is n times n minus 1 times n minus 2, right the way down through to 3 times 2 times 1. Then the denominator, n minus x factorial, is just going to be n minus x times n minus x minus 1 times n minus x minus 2, right the way down to 3 times 2 times 1. So there's a bit of cancellation which happens, okay? This cancels with this cancels with this cancels with this. So all I'm doing here is just considering factorials and the fact there's some cancellations which happen, which hopefully you should realise anyway from the choose kind of function notation, okay? So therefore I get this. Now let's basically now put in the 1 over n to the power of x. So let's multiply all of this by 1 over n times n over x, okay? So I've just seen that this first bit is just equal to this numerator here. Then if I'm multiplying by 1 over n over x, n to the power of x, this just goes on the denominator down here, okay? So therefore, if I multiply n to the power of x out, that's just n x times, okay? So n times n times n times n, x times, okay? So now let's have a look at this. So are you happy that there's going to be a way which I can write this? I can write this as n over n times by n minus 1 over n times n minus 2 over n. So basically every single thing that I'm multiplying by on the numerator gets stuck over n, because there's basically a way of matching the number of terms on the numerator is equal to the number of things which I'm multiplying by on the denominator as well. So I can basically write every single multiplier on the numerator as over n. Okay, now if I do that, and if I consider now the limit, so basically I'm saying, what happens as n approaches infinity? Well, basically, as n approaches infinity, each time will effectively behave like n over n. Why? Well, have a look. N over n is still there, okay, so that's just 1. But if I have a look at the next term, so n minus 1 over n, well, if I take the limit as n approaches infinity, basically what I'm saying here is I have a really massive number, take away 1, over the same really massive number. Well, if I take like 1,000,000 and subtract 1, then that becomes 999,999 over 1,000,000. Does that make sense? Because I'm basically sticking a really, really big number for n in here. So 999,999 over 1,000,000 is basically 1,000,000 over 1,000,000. Like, it's just going to behave like 1, okay? And the same for n minus 2. So basically subtracting like a really negligible number like 2, 3, 4, 5, 6, etc. from n, which is already a really massive number because I'm taking the limit as n approaches infinity, it doesn't matter. Each of these terms are effectively just going to become 1, okay? So therefore I just get loads of 1s being multiplied together. So actually that entire thing in pink up here, in the thing which I've written up here, my probability mass function, is just going to be 1, okay? That's just going to be 1, all right? Now if I consider the limit of the next term, so this thing in pink now, okay? So basically, I recognise this, so 1 minus some constant over n, all raised to the power of n. It looks a bit like the definition for E. Now, if you're interested in this, I have actually put a video on my channel which actually talks you through where E's come from. So if you have a look in, I think, week 6, intermediate mathematics, what are exponentials and logarithms, I actually derived this formula for you. So if you're interested in where this comes from, please feel free to have a look. Otherwise, I have put a video out there which is talking through where does E come from if you don't want to watch the hour-long video for that. Okay, so I've got a couple of videos which talk through this. Otherwise, you can just take my word for it that E is a special exponential number, which is 2.718, and it carries on forever and ever and ever. And this is the definition of it. It's basically the limit as some constant approaches infinity of 1 plus 1 over that constant, all raised to the power of that constant. Okay, it's just basically interest rate considered in the infinitesimal sense. Now, if I let n equal negative lambda over k, now you might sit there and think, why am I doing that? Basically, what I'm trying to do is make this thing up here in pink look as much like this thing as possible, because I can see it's close, right? It's just that it's off by lambda, okay? So it's really, really close to this thing. It's just that n and k have swatched places, and there's just a lambda on the numerator of this fraction. So what I'm trying to do is actually make this thing look as much like this thing as possible, then I can just replace it with e. Okay, so if I let n equal lambda to the power of k, then I basically take this, so just take this straight from here, and I basically get this. Okay, so if I replace n with negative lambda over k, I get this. Okay, which basically means I get something that looks like this, okay, and then basically means that I get this. So it's just basically using a bit of algebra, just noticing this, just substituting in, being a little bit sneaky, and then I basically can prove that that entire thing is just e to the negative lambda. It's a bit of a kind of a fudge, but it works, okay, it's totally true, and it's not invalidated at all. So basically that entire term, I can just say, is just e to the negative lambda. So now let's consider that last term there. Well, okay, if I take the limit of this last term here, would you be happy that as n approaches infinity, lambda over n should approach 0? So as I increase this, it should just basically become 0, okay? So in other words, I get this. So this should just basically be 1 minus something which is 0 to the power of negative x. Okay, because of course if I increase n, if I make n really big, because I'm taking a constant value, lambda, and I'm dividing it by n, which is a really big number, if I take a constant and divide it into loads and loads of little pieces and divide it by a really big number, I should basically just get that becomes 0. Okay, so therefore this thing here should effectively just become 0. So I get 1 minus 0 to the power of negative x, or just 1 to the power of negative x. Okay, so therefore if I do 1 over 1 to the power of negative x is just like 1 over 1 to the power of x. Well, 1 to the power of any constant number is just 1, okay? So the 1 to the power of any constant number is just 1. So 1 to the power of negative number is also just 1, okay? So that entire thing on the end there, that entire thing in pink on the end there, effectively just becomes 1, okay? So therefore, I basically said that if I have a large number of trials for a binomial distribution, which remember is the condition for getting a Poisson distribution, so to get from a binomial distribution to a Poisson distribution, just increase the number of trials, make them really, really big, then basically the probability mass function of a binomial distribution, as n gets really big, effectively just becomes this. And if I do a little bit of tidying up, I get this. And in fact, I could even write it like this if I wanted to as well. Okay, so all of those three things are fine. So what I've literally done there on the last kind of few slides, don't worry if you don't follow everything, you don't need to know everything. I've just kind of talked you through it in a quick place. Basically what I've said here is because the binomial distribution approaches a Poisson distribution as the number of trials increases, all I've done is just consider the probability mass function of a binomial distribution and then see what happens as the number of trials increase. So I need to first of all consider a rate. So instead of considering a probability, I consider a rate of success. Then I consider what happens as I take a large number of trials, and I've just derived that you get this. Okay, so I can basically say that for a Poisson distribution, the probability mass function is given by this formula here. Okay, now fortunately for you, this formula is on the formula sheet. Now, like I say, don't worry if you don't follow that. The important thing is that you just need to know that this comes from a binomial distribution in the limiting case as the number of trials increases, and you just need to know how to use this formula, okay? But I always say I'm educating you as a mathematician, as a statistician, so it's always good to be aware of where these things come from. So finally then, let's just have a look at some of these questions. So you can have a look at some of these questions yourself, okay? But actually I said that there was going to be a second kind of question to have a go at as homework. So the first set of homework for the weekly task I've already given you. Can you also have a go at this question for the weekly task as well, okay? So this question here, I want you to have a go for the weekly task, please. So finally then, let's just finish off on the expectation and variance. So what's the expectation of a Poisson distribution? Well, okay, I know lambda is the expected rate of success, right? It's the expected number of successes that I'm after in that given time interval. So therefore, if I look at this, I look at the probability mass function, the most likely outcome should be the one in the middle, which corresponds to whatever the lambda is, whatever the rate of success is. So in that case, E of x should just be equal to lambda, okay? Now, if I wanted to prove it, I can basically say, because it's discrete, the expectation of any discrete random variable should just be the sum of the outcome times the associated probability. Well, okay, I've got the associated probability up here, it's just this, okay? So basically, if I do sum of x times by this probability mass function, I get this. And if I basically expand this out, so I first of all stick 0 into this thing, then if I stick 1 into this thing, then 2 into this thing, then 3 into this thing, and keep adding them together, this is basically what I get. Let's see if we notice a pattern here. Well, okay, basically I notice that there's an e to the negative lambda in every single term. So let's factorize it out. Then that effectively just becomes 0, because 0 times anything is just 0, plus 1 times this thing, plus 2 times this thing, plus 3 times this thing. Okay, we'll have a look. Look what I can do on the denominator. Do you notice that 1 factorial I can write as 1 times 0 factorial? And 2 factorial I can write as 2 times 1 factorial. And 3 factorial I can write as 3 times 2 factorial. So let's have a look here. Basically what I can do is 0 plus each of these things. And then I can basically write this in terms of lambda, because that there is just going to become lambda. That there is going to become lambda squared, and then the 2's are going to cancel, just become over 1 factorial. 3's are going to cancel there, so it becomes lambda cubed over 2 factorial, and then lambda to the power 4 over 3 factorial, etc, etc, etc. So basically what I get if I factorize out a lambda is this thing here in the bracket. So I've just literally factorized a lambda out of this, okay? So I've cancelled off the 1, the 2's, the 3's, and I just basically factor out a lambda and I get this, okay? Now this sequence here is really important. It's the Taylor series expansion for each of the lambda. Now we will look at Taylor series expansion, but it would be after Christmas, okay? So just trust me for the moment that this thing here is a Taylor series expansion and it's equal to e to the power of lambda. So in other words, this thing in pink is just e to the power of lambda, which means I get e to the negative lambda times e to the lambda. Well, if I have e to the negative lambda times by e to the lambda, effectively these powers just add together, so I get e to the power 0, which is just 1, so therefore this thing here should just be lambda. So it's 1 times lambda, which is just lambda. Therefore I can say that the expectation of my Poisson distribution should just be the rate, it should just be lambda, okay? If I do the same thing with a variance, well, all right, so I know now that the expectation is equal to lambda, so I can use my traditional formula for my variance. A variance of x equal to e of x squared minus e of x all squared. We proved that in the last video, okay? So now, because the denominator of the probability mass function is effectively r factorial, it's effectively x factorial, whatever your rate, whatever your probability of success you want to be, okay? So it's just x factorial. I can write that as r times by r minus 1 times r minus 2. So therefore, it might be easier to write this as this, okay? So I can basically say that because I have e of x squared minus e of x, basically what I'm looking for is something take away something. So I'm going to basically write this as e of x squared minus x. Those two things are the same, okay? Can prove to you those two things are the same, which then I can factorize x squared minus x as x times by x minus 1, okay? So therefore the variance should be equal to this, which I can write like this. So I'm just keeping this fact up here in the right hand corner. But for the moment, what I'm going to do is use a little bit of a trick. I'm going to basically try and make this look as much like this. So basically what I'm doing, instead of having the squared, I've got the e of x squared minus e of x all squared, and then I'm going to basically take away and add e of x. Okay, because if I do that, basically there's 0 in the middle. So the stuff in pink wasn't there at the start, and it's still not there. I've just basically chosen to write it in instead. Okay, so now what I can do is, you see here that I have e of x squared minus e of x. Well look, e of x squared minus e of x is just e of x times by x minus 1. So I just replace that first two terms with this and keep the other two terms the same. So now what I can do is, if I expand the e of the x times the x minus 1 out, basically I know that expectation is just whatever goes inside the brackets times the probability of success. Okay, so therefore if I replace this with this, so the x times by x minus 1 with the x times the x minus 1 in my formula, then what I can basically say is the probability of success is still given as this. So if I substitute that back in, then basically what I can do is write x factorial as x times by x minus 1 times by x minus 2 factorial. That's the reason why I wanted to do that, okay? Because now I've got the x times x minus 1, that cancels with the x times the x minus 1 from my x factorial. So I'll just be left with x minus 2 factorial on the denominator. So in other words, I'll get the sum of lambda to the power of x e to the negative lambda, all divided by x minus 2 factorial. All right, fine. Now, because I know that e to the negative lambda is constant, then basically I can pull that out the front of my summation. It's not going to make a difference to my summation, so let's just pull it out. So now what I'm going to be left with is effectively this thing. So if I stick 0 in here, I get lambda to the power of 0 over 0 minus 2 to the all factorial, okay? And I keep going, okay? So I keep going all the way through. So now I stick 1 in, and then 2 in, and then 3 in, then 4 in, then 5 in. Well, are you happy that if I stick 0 and 1 in, this thing here is effectively just going to be 0? Because I'm going to be trying to do a negative factorial on denominator. And in the context of this discussion, we're not interested in negative factorials. So therefore, it's just going to become 0, okay? But then I'm just going to be left with lambda to the power 2 over 0 factorial, which is just 1. Then lambda to the power 3 over 1 factorial, etc., etc., etc. Okay? So what I should be able to do now is factor out a lambda to the power of 2. So if I factor out a lambda to the power of 2, I basically get this, okay? So factor out lambda squared, I effectively get this, okay? And you should recognize that, again, that is just e to the power of lambda, okay? So I get e to the power of negative lambda times lambda squared times by e to the lambda. That's what the e of the x times the x minus 1 bit means, okay? Always just lambda squared. Okay, so let's come back to this then. So basically just where I left off was here. I've just worked out that this thing here was just lambda squared, okay? But I've still got e to the power e of x minus e of x squared. Well, look, I know e of x, don't I? I know it's lambda. And therefore, I also know what e of x squared is, because it's got to be lambda squared. So in other words, I've got lambda squared plus lambda minus lambda squared. Lambda squared just cancel, and I'm just left with lambda. Okay, so the variance of x should just be lambda. So basically, those last few slides, you don't have to understand everything about them. Basically, I'm just giving the proof of why they're true, because it's a little bit gnarly and it's good mathematical practice to do it. Okay, so basically what I'm saying here is the variance of x should just be lambda. So in other words, for a Poisson distribution, we have the probability mass function given as this. And again, apologies that the green has kind of been chroma keyed out, but hopefully you can read it. Okay, and we've got it on previous slides if not. We've also just proved that the expectation of a Poisson distribution is lambda, and the variance of a Poisson distribution is also lambda as well. Okay, so that's basically it. Okay, that's basically what you need to be aware of. Okay, so you've got now Poisson distribution and binomial distribution all in one. Please make sure that you have a go at those two activities for this weekly task, so upload those to Flipgrid as well, and that will be it for probability distributions. In the next video, we're going to move on to continuous distributions, and we're going to look at the normal distribution, which is probably the most important distribution of the lot.